my honor to introduce today's speaker, Dr. Shital Poudyal, who is an Assistant Professor and Ornamental Horticulture Specialist at Utah State University. His research focuses on developing sustainable management practices for landscape and nursery plants, emphasizing on water conservation. He aims to evaluate and understand physiological, morphological, and biochemical responses of various ornamentals subjected to irrigation with unconventional water sources and develop effective techniques to protect surface and groundwater resources by reducing agrochemical runoff. So without further ado, welcome Shital. Thank you so much for joining us today. I'll let you take it away.
Thank you, Katie, and welcome everyone. I think people are still joining in, and as they join in, it's 1:31. So yeah, it's great to see you all here. And today I'll be talking about the agrochemicals in irrigation return flow and how they affect plants. So this is a very crucial step and crucial thing to understand when we are recycling water. So without further ado, I would like to share my screen here with all of you. And then sharing. So Katie, how does it look? The screen looks good?
That looks fantastic, Shital.
Okay, good. So yeah, because it's the summer is creeping on us, I think from the next time, like in next few months, we'll just hold on our regular monthly webinars for the busy summer months, and then we'll kick back on. But then these are always recorded, so people can go back and watch it. Although I would really love to have you all be here, and this would give the chance to interact. So I truly admire people joining here, although you have your busy summer schedule. Without further ado, let's move on. So again, as I said, today I'll be presenting on agrochemicals in irrigation return flow and how it affects plants. So the learning objectives for today would be about the types of agrochemicals that can be present in irrigation return flow. So when I talk about irrigation return flow, it's the runoff water from nursery or landscape. So that's what I mean when I talk about irrigation return flow. So what kind of agrochemicals can there be present in that irrigation return flow? What properties of irrigation return flow or what properties of agrochemicals make it more likely to run off or leach and then collect in the retention pond. I'll also talk about fertilizers, its concentration in irrigation return flow. What are its implication as well? Also pesticides that can be found on irrigation return flow. And I will also give a brief introduction to how to reduce those irrigation return flow, how to reduce those agrochemicals, in the irrigation return flow. So moving in, although the drought map looks a lot better now, this was in the start of year 2022, we're still under, like most of the states were still under drought. Now it's getting better, but the restriction and the water price are surely going up. Utah is metering the secondary water now. It's ongoing process, and it was a long due. So even if the nursery or landscape are using secondary water, it's going to be metered. The big nursery here in Utah are using culinary water or the municipal water, which has a huge cost associated with the water or the irrigation. So yeah, we are facing water shortages, and the water prices are going high. Also, you can see in this map here, all these in red are somewhat impaired water, meaning this water needs to be cleaned or remediated to improve the quality. So more than 50% of Utah's waterways, or around 50%, remain impaired or polluted. And when we talk about the pollution here, non-point source pollution are one of the leading cause. They are the leading cause in the US. water, rivers, and lakes. Also in Utah, they are one among the leading cause of water impairment. And non-point source pollution are largely attributed to agricultural water use or agricultural operations. So what is the problem with the non-point source? Like what is the problem associated with it? There are a lot of problems with nutrient runoff. We get algal bloom, we get nitrate in the water, which is not drinkable when if we have nitrate in it above a certain concentration. We also have pesticide. We might have pesticide in the runoff water, which is toxic to aquatic lives. We might have pathogens. There are governmental rules. Even in Utah, there is a limit for the amount of nitrate or phosphate you can have in your water before you let it go to your wetland. So there are a lot of problems associated with the runoff water. And if we trap and reuse it back, we might get steady water supply, will reduce the pollution, so we are not polluting our watershed and water systems. We can get an environmental friendly tag. And then I have research ongoing and works ongoing to see how can we harvest the benefit when we go environmentally friendly, meaning if we use sustainable practices, how can we market the crops accordingly? So a consumer would prefer paying higher prices for the product. Also will reduce the amount of water use, and that would also be a lot of water saving. Steady water supply is really challenging here in Utah. With ongoing droughts, the water districts and the water agencies cuts the water supply and limits the irrigation to certain number of days. There are broken water lines, things like that. So it's always good to have a steady water supply. Now, we can do this, we can harvest the water, retain the water, reuse it back to the plants. But there are some problems that are associated with irrigation return flow, like recycling those water back. The first and one among the most is the changing in water quality, such as oxygen level, pH, like increased pH, increased electrical conductivity. So those are some of the problems, and I'm not going to talk about all of these today. If you want to know more, if you go to this link here, Clean Water 3.org videos, it'll talk about the water quality, oxygen level, pH, ECs, and you can watch those. The problem also arises with the algal blooms with high nitrate and phosphate concentration in runoff retention pond. We might get algal blooms, and that might be something we need to consider, like remediating in the retention pond. We also can get suspended solids other than, so suspended solid is anything like sediments or soils or anything as such. The number one priority or the number one problem that can arise is pathogens and disease. Again, if you go to these videos here, it will talk a lot about pathogen and disease. And we'll also bring someone to talk about the pathogen and disease in future webinars, an expert on those field in recycling pond. But then that's the number one thing that you need to consider when you are using recycled water. And also agrochemicals, chemicals such as fertilizer and pesticide. If not the top, it is a few among the top concerned when we are reusing the recycled water. So we will talk today, our presentation, we will discuss in detail about the agrochemicals such as fertilizer and pesticide present in irrigation return flow. So moving in, fertilizers in irrigation return flow. What kind of fertilizers can be there? These are some of the kind of fertilizers that can be present in irrigation return flow. So this is a trial from Michigan State University. I was leading this trial. You can see the pH is slightly higher on the high end. But the salts, when you see in the irrigation water and the runoff water, it was not too bad. So even the runoff water had that salt level within the range. But when we look at the nitrate and ammonia and the phosphorus, nitrate and ammonia. So the total nitrogen we saw was a little bit higher compared to what we had in the clean water or the fresh water. When we look at the phosphorus, it was slightly higher, not significantly higher. Potassium did increase. And then we saw increase in calcium, chlorine and sodium. So this was what we saw. But what we can see, this is the research from various nurseries. And then the total nitrogen and total phosphorus in irrigation return flow water. So the water in irrigation retention pond or the irrigation return flow water ranged anywhere from 8.3 to 21.7 milligram per liter for total nitrogen and 1.4 to 8.3 milligram per liter for phosphorus. So you can see this amount of phosphorus is even sufficient to crops. Most of the crops applying around 5 to 8 milligram per liter of phosphorus is enough. So, and then this would and then the nitrogen around 15 to 20 would be good level. But although we need to increase and go higher on that, depending on the crop type and how many applications you make, but still this is a very good level. Now, there are few things that we need to consider with these amount of nitrogen and phosphorus. We are talking on nitrogen and phosphorus because those are the two fertilizer elements that are crucial in keeping our watershed clean. So when we have regulations, those regulations are pretty much on total nitrogen and total phosphorus. And also they are the major compound when we use them for irrigation, or when we use them, they are the major compound for plant growth, or the major elements for plant growth, sorry. So if we have these amount, the implication would be one, we could reduce the amount of fertilizer that we apply. And this would come with a major cost saving. Two, we can have negative impact such as algal blooms in our reservoirs or in the retention pond with this amount of nitrogen and phosphorus. So we might need to control that amount, or we might need to lower that amount if we're storing those water in a retention pond. But then again, it might be benefit to the plant, but and then if we're releasing water to the watershed, we might have to check those levels and go down below so that we can sustainably let that water go to the wetlands. So moving forward, for a specialty crop producer, when we talk about any kind of landscape growers, when we talk about the properties of nitrogen and phosphorus to consider, these are some of the properties like solubility. When we talk about solubility, nitrate is highly soluble. Ammonia is less soluble, and phosphorus, it varies depending on feedback. So this phosphorus is complicated. So anything that is highly soluble would easily leach down with water and go to the retention pond. If we do not have the retention pond, it might go to the wetlands. So we need to consider nitrate as a high leaching compound. Ammonia, it might not leach as much as nitrate in the water. It's less soluble, so it has less probability of leaching. Phosphorus, it might leach, it might not, it depends. But again, the probability of phosphorus for leaching with water is pretty low. We look at the sorption capacity. Now, this sorption capacity is the ability of those compounds to attach with the soil particles or organic particles that we have in the substrate. Nitrate has very low sorption capacity, so it doesn't bind with the compound, it just moves freely with the water. So again, the probability of leaching with the water increases. Ammonium, while in other hand has high sorption capacity, so it attached with the soil particles and it's held by those particles. But again, if we let the particles move with the water, it will also leach or move with the particles. Phosphorus, it binds highly with the soil particles, or there are phosphorus available or binding with those soil particles. So as the soil particles move, it moves as the soil particles move with the water, it moves with the water and collect in the retention pond. So that's something we need to consider. Release. So nitrate is released pretty easily. So now rapid release, meaning plant would get it faster. Also, it would leach faster. Ammonia and phosphate, while other hand, are slower release, are again phosphorus. So with the phosphorus, there is a pool of phosphorus that is soluble and insoluble. Now those pool changes based on feedback mechanism. So once the plant take up phosphorus and the soluble phosphorus is depleted, the insoluble pool would make more phosphorus soluble. And then, so it's a feedback, and it's way complicated than I told you just now, but the basic understanding is it maintains that pool of phosphorus in the system. Again, the charge, we know soil is or the substrate is usually negative charge. So nitrate is also negatively charged. So the soil cannot hold the nitrates. It will just leach down with the water. Whereas ammonia can be attached to the soil particles or the substrate particles. So leaching with water is reduced, but then it can always leach with the soil particles or the substrate particles. Phosphorus, again, is negatively charged. Usually the form that plants takes up on, it's a negative, so it can be sent back. But those pool of phosphorus, again, as I told you, phosphorus is complicated. There is this soluble pool and insoluble pool, and those that keeps changing. So just understand that phosphorus has high probability of leaching with the substrate rather than leaching with the water. Now, what happens if those substrate move with the water and goes to retention pond? As I told you, if it goes to the retention pond present in nursery, it can have algal bloom and eutrophications. If it goes to the watershed, rivers or lakes, it might bring problems, a lot of problems. So this is a picture from Utah Lake, and it was adapted. I adapted this from Salt Lake Tribune, and you can see how the algal bloom is causing the water to be polluted, and if we have harmful or toxic algal bloom, we can't even use that water with after treatment. So it's complicated problem. Once we have those problems, it's complicated to rectify it. So we better be careful. Now, phosphorus can move with both water and sediment, but mostly with sediment. Nitrogen, on the other hand, is dissolved with water, but it can also move with sediment. Now, how can we rectify it, or how can we lower the probability of those fertilizer running off from our system? Or even in some cases to lower the amount in retention pond if the problem is in the retention pond. Use slow release fertilizer. The fast release fertilizer or water soluble fertilizers tend to be released immediately after application. So the amount that plant takes it just takes it, and then any amount that plant do not take it just goes down, it leaches out, and it goes to the runoff. So if we can, it's always a good idea to use slow release fertilizers. Mix with fresh water during storage at retention pond. So if the potassium, phosphorus and nitrogen in the storage pond or the retention pond are higher, and it's causing problem, we could use some fresh water in there to mix it, and then lower the concentration and lower the amount of algal bloom or any problem associated with those runoff. We could also, if the sediments is a problem, we can always catch the sediments with the fine mesh or some screens or filter stripes before they reach the pond. High evaporation here in Utah may increase the amount of nitrate and phosphate may increase the concentration of them in the retention pond. Or even if the water evaporates, it's no use. We can't use that water to apply back. So we can use storage tanks instead of the retention pond, like huge storage tanks. So we collect the water from the runoff, we push that to a storage tank, and it would be stored in a tank. Again, we can use filter stripes. Filter stripes are the stripes where we can fill those bags with the substrate of our, with the material of our choice. We could use wood chips, we could use any other materials like carbon filters, materials in those stripes, and let the runoff water go through those stripes before it reaches the pond or the wetland. We can also use wetland filter stripes, meaning we can use plants, strips of plants or wetland plants, let the plant water run through those wetland plants before it reaches the retention pond. And then that way, so in this picture, you can see when we use the wetland filter plants, as the length of filter plants increases, the amount of phosphorus trapped is increased. So if phosphorus is a problem, we could always use wetland filter stripes. It works even for nitrate or nitrogen, and we can reduce the amount of those fertilizer in the retention pond. Now, these are about the fertilizer like nitrate and phosphate. In most cases, these are beneficial because it reduces the amount we need to apply to the plant. If in case it's a problem, these are the way how we could lower the fertilizer. Let's move on to pesticide now. Pesticide. So pesticide include herbicide, fungicide, insecticide, any kind of anything. It's a broad term. It doesn't mean something that kills pest. It also means something that might kill weeds or plants. So when we talk about pesticides in irrigation return flow, what we need to consider is the properties of those pesticides. What are the properties of pesticide that makes it more responsible or more liable to be found in retention pond or in runoff water? So let's dive in. Then the first thing is solubility. As like fertilizer, pesticide also has a different level of solubility. The solubility is just the potential of a pesticide to dissolve in water in this case. So highly soluble pesticides are likely to dissolve with the runoff irrigation water and move with runoff water to the containment pond or a retention pond where its concentration might build up. So pesticides like asphate, glyphosate, mefenoxam are highly water soluble. And if you are using those on the plants and collecting the runoff water, better check out for those pesticides in the retention pond. Now, some pesticide might have very low solubility, and they would be less of a concern compared to these. The second thing we need to consider is the sorption coefficient. Adsorption or sorption coefficient, KD, is just the measure of how well the compound bind with the soil particles. Now, in nursery and landscape industry, we deal with organic substrate. Our substrate has a high amount of organic compound. So we do not mostly consider KD, whereas we considered KOC. So the sorption of those compounds with the organic substrate. So any pesticide that has high KOC adheres to the substrate particles, like it adheres to the substrate and it adheres to the ground, soil, hence the movement with the water and the potential for leaching to the retention pond is low. So low. So if the substrate has low KOC, meaning it doesn't bind well with the substrate particle, then it might move easily with the water. Bifenthrin, chlorophyrippus is banned. It was banned and then it was re-released in the Trump era. And I don't know what's the deal with chlorophyrippus right now. But anyway, it is highly soluble. Remind me. So it's highly soluble and we need to consider this compound. Let me go through the chat and see what people are talking about. Reminds me of how vitamin D is needed to absorb calcium in our body. This is the most fascinating class so far. This is how long have they been doing this study? So we did the study in Michigan for 4 years. We didn't see any damage of pesticide in those plants. I'll talk about it later on. But then people have been doing this research for more than 10 years now. And we have documented lot of things about this movement in return flow. So moving forward, the next thing is half-life. So we need to consider the half-life as well. Half-life is the time it takes for a pesticide to reduce to half of the concentration that was initially there. So if we apply 1 milligram per liter of isohexaben, how long does it take for the isohexaben concentration to reduce to 0.5 milligram per liter? So as we all know, materials degrade, elements degrade, and the pesticide made of different elements and compound degrade naturally, and the degradation are facilitated by sunlight, microbial degradation, temperature. There are a lot of like biological activity. Those all degrade the pesticide in a system, and this differs at different environment. So a high humid environment would have high microbial activity, so microbial degradation would be faster versus to pesticide applied at arid climate where degradation through microbes might be lower. But then if the pesticide is degraded by the sunlight, it would be higher in maybe in the arid or high intensity sunlight receiving regions versus anywhere which is mostly cloudy. So we need to understand the half-life when we're working with the pesticide, when we are trying to understand the dynamics of pesticide in irrigation return flow. Based on half-life, pesticides are classified as persistent with half-life of less than, non-persistent with a half-life of less than 30 days, moderately persistent 30 to 90 days, and highly persistent more than 90 days. Pesticides such as isohexaben has half-life of 2 to 6.6 months. Again, its degradation and half-life differs depending on the climate. Oryzalin 1.4 to 4.4 months, and oxyfluoroquine is 1 to 6 months. May have long half-life. Therefore, these pesticides they can still be present in months, even after months in retention pond. So we need to consider this. So any pesticide that has lower half-life, you might be okay with using that retention water maybe after a few days of collecting it. The other factor that we need to consider is vapor pressure. Now, this vapor pressure is interesting and a little bit different from all others because it's the potential of a compound to evaporate. So in a general condition, pesticide like chloropyrifos and trifluomazole, they tend to evaporate. And what happens is, say you have a nursery, you are using these compound, even if in retention pond or you are just using it, they have a tendency to vaporize and affect field across the road or just across to your nursery. So when we're applying a pesticide with high vapor pressure, we always need to consider the wind drift and sun and things like that. And also in retention pond, if these compounds are being collected, they might vaporize and affect the nearby vegetation. So you better look out for these kind of pesticide with vapor pressure of less than 0.000001 mmHg, so milligram of mercury, are less volatile, whereas any pesticide with high mmHg are highly volatile. So look out for this. Now, when I tell you to look out for this, you might be thinking, where do I look out for this? Or how do I find this out, right? And there is a very easy way to do it. Just Google your pesticide name and type SDS, safety data sheet, or material safety data sheet. A lot of the nursery even might know this. They might need to keep this in the stack with the paperwork for the checks and things like that. But if you Google pesticide name and SDS, you'll get something like this. So this is for asphate, 90% WDG. So this is the type of formulation, and it was made by Loveland Products, and they have this data sheet. And this data sheet is usually 3-4 pages long. I don't have the time to explain all those things in there, but you go in, you read this through, and it will have the solubility, it will have the vapor pressure, It will have the half-life and everything that I discussed, and a lot more. Also toxicity and how you store it, where do you, a lot more than that I talked about. So this is how you find those out. It's pretty easy, right? So now, these are the properties that might influence or that might make pesticide more or less likely to be found in the retention pond. So let's look at an example here. So pesticide concentration depends on pesticide properties. Now, when we look at, so concentration in runoff depends on solubility, half-life, and other things. Here, I looked at the solubility. And when you look at the aspect, glyphosate and mefenoxam, their solubility is higher among all these. And so we see the dilution of this in the runoff or in the retention pond is 2,000 to 5,000 times. So even with the pesticides that are highly soluble, this was in context of Michigan, but it might be similar here in Utah. If you store the water in tank, but with evaporation going on, it might be 1,000 to 3,000, might be a little lower dilution, but still we are getting that dilution somewhere from 2,000 to 5,000 times, even for highly soluble pesticide. And this was in the field conditions. When you look at these are mid-soluble, and these are further diluted. They are diluted to 25,000 to 50,000 times. Now, will this concentration from the runoff affect the plant? Probably it might not, right? We need to see. But again, I'll talk about how these concentration will affect plants. But again, look at this number here, 2,000 to 5,000, 25,000 to 50,000. If you look at some of these pesticides, which are very less soluble, prodiamine and bifenthrin, we didn't detect any of these in our retention pond. Although we applied 198 gram per AI per hectare, 3 gram per AI per hectare, we didn't see anything in the retention pond. So it all, so you can understand the importance of solubility and other things here, right? So how does a pesticide flow to retention pond or a collection pond? Pesticide flow to retention pond is very low from a container leachate due to binding with soil substrate. Usually, pesticide bind with this substrate here in the container. So even through the leaching, it doesn't go beyond the container. Most of the pesticide that we collect in the retention pond are because of non-target pesticide application. So if the pesticide, so we know when we have containers in the nursery or any plants, they are spaced apart, right? So when they are spaced apart and we make a blanket application, most of the pesticide or water lands on the non-target places, not in the container, but in that zone, in that soil or in the landscape fabric. And when we irrigate, those pesticides are most likely to move with the water to the retention pond. And once it moves, it peaks shortly after application, and then it decreases because, again, because of microbial degradation, sunlight degradation, a lot of other things going on. So it is better to withhold from applying runoff water immediately after you spray on those containers. If you hold for a few days, it'll get diluted, and then it is less likely to cause any problems. Now, I talked about all these factors that affect this concentration on the retention pond. Let's look at the concentration itself from a real world scenario. I showed these are the real world cases as well. But when we look at the concentration, usually it's found in parts per billion. Sometimes parts per million, ppm or mg per liter, but when it's in that amount, it's less than 1 ppm. So when you look at this figure here, I adapted this from one of my papers that I published. But when you look at metachlor in irrigation runoff, it was 7.8 parts per million. It was in the runoff, but when in the pond, it went to the pond, it gets further diluted, right? So these I adapted from various papers. So these are the citation for the papers that I adapted this from. But when we look at the containment and retention pond, trifluorine isoxaben, it's around 5 parts per billion. 55 parts per billion. We look at the oxyfluoropyr, it's less than 1 part per billion, ornamental less than 1 part per billion. So runoff near production area. And then when we look at the oxyfluoropyr, again, this different other paper also found same, it's less than 0.1 parts per billion, but this concentration might have implication. They might affect the plant. I will talk it as I move on. But again, when you look at the pendimethalin, it's 4 parts per billion. So most of these in the retention pond are parts per billion. In runoff, immediately after application, it might be in parts per million, but then this is all immediately after application. So it gets diluted in the pond and the concentration reduces. So these are the concentration found. Now you know what properties to look out for. You know how they lead to the retention pond. You know how much, like a ballpark of how much what concentration might be present in the retention pond. How likely is it to cause injury to plant? Because the last thing that we want is to cause injury for the plants, right? So it depends on a lot of things, but here I boiled them down to four or five aspects. Number one is pesticide type. So when we say pesticide, it includes herbicide, it includes insecticide, it includes fungicide, and a lot more, right? So herbicide is usually more damaging compared to insecticide or fungicide because it has same mode of action as plant. So herbicide are designed to kill weeds or plants, right? So their mode of action, such as oxyfluoropyr, what it does is it disrupts photosynthesis, or it causes photooxidative damage on leaf. And then once the leaf is discolored or it has damage, it's not able to photosynthesize properly. Now, this is something that can affect our target plant as well, right? Target plant. Ornamental, it disrupts cell division, meaning it restricts the cell division in plants so plant can divide well, the leaves can divide well. Whereas pesticides like insecticide and fungicide are targeted to kill the animals or the insects or the fungus. And fungus has different physiology or different mode of action which might not be present in plant. So anything that is not present in plant, how would it affect plant, right? So usually it might, but usually insecticide or fungicide are less damaging compared to herbicide residues. Now, post-emergent herbicide are more damaging compared to pre-emergence, because when we're spraying this plant, these plants are already immersed, and any herbicide that is post-emergence acting would damage more to those plants compared to pre-emergence. Now, when we look at the examples, there was this large phytotoxicity trials by Mathers and his team. And when they look at the damage, rose was sprayed with isoxaben and ornamental in field and then they did see those phytotoxic damage. But when they sprayed the same plant with indazifam, they didn't see any damage. So you can see it depends on pesticide type. What kind of pesticide did they use? Again, at the same concentration, isoxaben had greater impact on growth and photosynthetic parameters of semi-aquatic herbaceous perennials compared to ornamental. So in this case, we saw in semi-aquatic perennials, this was the research done by Thomas Fernandez in Michigan, and he saw that isoxaben was more damaging compared to ornamental. Now it can be vice versa. Again, it depends on plant type as well. But again, you need to consider the pesticide type. So if you see no damage on one pesticide, it doesn't mean the other type of pesticide wouldn't cause damage. You need to consider that. Let's look at some photos. So these are the plants that has been treated with isoxaben. There were no damage observed on hydrangea, cornus, or hostas. When we also sprayed with the chloropyrifos, different concentration, these are for the highest concentration, we didn't see any damage. Of course, this was when the chloropyrifos was legal to apply. When we used oxyfluoropyr, this was 0.02 parts per million. So it's pretty low. We could see this damage. Look at the plants. So again, look, we need to consider what kind of pesticide we are using and what kind of pesticide are present in our retention pond. Also, potential for plant injury depends on plant type. So with same oryzolene at similar concentration, dwarf gardenia, we didn't see any effect on either root or shoot. Fresh wet was same regardless of the concentration sprayed. And in this fountain grass, we did see at the concentration 1000 microgram per liter. We did see reduction in both shoot and root weight. Same pesticide, different plants. We did see that damage. Again, look at this oryzolene concentration. Fountain grass, 1 mg, no damage. 10 mg, we did see a lot of reduction in shoot mass. But when similar application in daily, we didn't see any damage, even at 1 or 10 milligram per liter. So I hope you are getting these things. So it's also depend on what kind of plants you have. It's not always pesticide type. It's kind of plant that you have as well. Let's move on. So this is cornus. When we look at the concentration, so this is for oxyfluoropyr. This is the black is 0 milligram per liter. The white is 0.005 mg per liter or parts per million. The highest, this one is 0.02 parts per million. You can see the damage here. Hydrangea is having a lot of damage. Hosta, similar, it's having a lot of damage, but cornus, it's not having that much of damage. Of course, when we go to 0.2, it's a damage. But then again, hydrangea. So here we can tell cornus is pretty much less susceptible to oxyfluoropyr damage compared to hydrangeas or hostas. Same graph, we can look it at different angle. Look at the dose dependent. So the damage is also dose dependent. If we have 0.005 milligram per liter, we didn't see any damage in hydrangea. But then if we increase, the damage to the leaf is increasing. Same for hosta, same for cornus. So it's only not only pesticide type and plant type, it's also dose dependent. How much do you apply? See here. So these are susceptible at lower doses at 0.01, but then cornus is only susceptible to 0.02 milligram per liter. Let's look at some pictures again, because pictures are the best, right? It just speaks for itself. So when we look at the plant sensitivity of hydrangea, oxyfluoropyr, this is no application. It's not receiving any pesticide. It's growing healthy. When we go to 0.01 parts per million, you can see this damage. 0.02, a lot of damage. Hosta, these are how plants were looking. 0.1, few damage in the leaf, but when we go to 0.02, it's a lot of damage. Let's go to cornus, dogwood. No damage, a little bit of damage, pretty more damage. Now, so it's dose dependent, not only from this study. Look at this study. I think this was in a different crop. It was in sorghum and it was a field research. Carbofuran and quinalphos both reduce shoot weight at higher dose. So when we have only 0.5 kg per hectare application, no damage. But again, if we go to 10 kg per hectare, we did see some pretty significant dry weight reduction on shoot. So understand it's dose dependent. Again, here we look at this picture, carbofuran, quinalphos, same study. Effect is dose dependent. Also the repeated, if we make a repeated application, I think I have that slide somewhere. So let's move on. It depends on pesticide type, plant type, dose, and also growth stages. So if you look in this figure, I know it's a complex figure, but bear with me, I'll explain it to you. This GS5 is growth stage 5 when the plants had fewer leaves. This is the second growth stage 15. So this is 10 days after it sprout. This is 5 days after the plant started producing leaf in hydrangea. This is 15 days after, this is 25 days after, and this is 35 days after. This was when the plants were exposed. So when the plants were exposed to oxyfluorophene at 5 days after leafing, we can see a lot of damage. But then we applied it once and then we stopped. We let the plant to recover. Then after 20 days, plant recovered pretty much well. They were recovering well. But then 15 days after, the damage was not as high, but then recovery was also slower. The more we move on, the damage, immediate damage is lower, but then the recovery is also lower. So what we can get it from this is early growth stages are most sensitive to those residual recycled water pesticide application. But then it also has a rapid recovery. So if you were to use that water anyway, and then you will be having those plants for more than 20 or 30 days, and then you will sell after that time, it's more like it's better for you to apply that water in early growth stage versus later growth stage. But if you will be selling that plant pretty quick, don't apply at early growth stage. Apply at lower growth stages of the plant, so you have the least damage. So early growth damage has more, or during the early growth, there is more damage, but faster recovery. Why? Because most younger leaves absorb, retain, and translocate those pesticides at higher rate because they have thinner cuticle, thinner weight, wax. But then as they grow on, they have that rapid growth, and then the recovery is also faster. Let me go on to the chat again and see what's going on. I did put a question in Q&A section. So more established plant were better when exposed, depending on the plant. Yes, Kelly. The more the plant mature, the less is the growth. What is the red not participating? Why is the red not participating in the study? So chlorine at much higher level has no effect. So again, I'm talking all these in context of the ornamental plants or the landscape plant. When we go to eatable crop for consumption, that's whole different environment. You might not even be eligible to apply recycled water for crops like basil or something that you eat if you have these pesticide in it. So today in this topic or throughout this presentation, we'll be talking in relation to plants that are not for consumption. I'm so sorry I didn't make that clear earlier, but I think you got it now. So you can see again, not only on the growth stage, but the pesticide that are residual produce effect immediately, or it may produce a lagged effect. So these were the GS15 plant, meaning they received one application of oxyfluorophene or oryzolene 15 days after the sprouting, and 10. These are the plant that how they look 10 days after the end of. So these oryzolene plants are pictured 10 days after the exposure, but these are 1 day after exposure. So oryzolene produce effect, or the maximum damage is seen after 10 days of application. So it has that lagged phase when you apply and when you see, because it damages those cell division and the cell doesn't divide, and that the result is seen after 10 days. That was when the damage was at the peak. But for oxyfluorophene, the peak was 1 day after application, immediately after application. So you also need to consider that when you factor in things. When is the pesticide producing the most damage? Also, the length of exposure. Applying once versus continuous application, we can see the repeated application of those residual concentration, it builds up and it has more damage. So this is single application, this is double application. The double application, we saw more reduction in dry leaf in both pesticides. So if you are constantly applying, it might produce more damage. So if you can alter like recycled water and fresh water and recycled water and fresh water, so reducing that repetitive exposure might do some benefit. But again, these are all in case those agrochemical produce damage. It's very unlikely. The chances of producing damage is minimal though. So this was research at Michigan State University that I was leading. So we had these beds, and then we had collected runoff water, and then we also had this bioreactor and retention pond, and then we had this evaluation bed here. In field condition, because of the sunlight and microbial and rainfall and all those things, the degradation of pesticide and agrochemicals are higher. So it might produce lesser damage compared to the greenhouse production site. So this was the field, this was the evaluation bed. This was the runoff bed that had been sprayed with 10 different pesticides at different intervals. Yes, that was me doing this in a hot July when it was 98 °F. And I was boiling inside there. And this was the retention pond. And we were testing the proof of concept to see if it works. And this was the bioreactors, that's a wood chip and kerosene clay bioreactors. And this was the water collected after the bioremediation treatment. So what we saw again was these were the pesticide applied at these rates, and we didn't see any damage. We didn't see any damage produced by those pesticides. So from this, we found out that either the remediated water or non-remediated, just the retention pond water, it was good for our plants compared to the clean water. We didn't see any effect on the plant. And I must tell, all of these are ornamental plants. We are not using these for edible purposes. These are just for the landscape plants. So these, we didn't see damage, but that doesn't mean there is not going to be any damage. And this presentation, I am making sure that you know what to do in case you have damages from agrochemicals. How do you reduce that? So how do you mitigate potential risk? Although the risk is lower, there are risks. So what we can do is, when we are applying pesticide, granular formulation has more seed flow. So when you randomly apply granular pesticide, it can easily be carried by water and run up in higher concentration. So it's better to apply a soluble formulation rather than the granular formulation. But again, it depends on pesticide. For isoxaben, there was high runoff with granular formulation, but for trifluorine, it was similar. Either you apply granular or spray. But again, shorter irrigation cycle. So if you can go with cyclic irrigation, so going once and stopping and then making second application. That way the pesticide can get adsorbed to more soil particles, and then it's less likely to run off. Less soluble pesticide can lower runoff concentration. So if the pesticide is not soluble, it will less likely to be run off and then collected in the retention pond. Non-penetrable fabrics such as plastic, like the fabric that we use in nursery growing location, if we have non-penetrable fabric, then the pesticide is less likely to adsorb and it moves on, and the concentration in the retention pond might be higher. Whereas if you have a gravel or a landscape fabric, the pesticide can adsorb in there, and then the movement is lower. Instead of doing a target pesticides application, instead of doing a random bucket pesticide application, it's better to go onto the target plants and target zones, so you have less pesticide present in the system. So if you have a shorter pesticide with shorter half-life, just when you collect the water, you can let that water sit in there for a few days before applying, so that the pesticide degrades in there. And also sensitivity is species specific. So whenever you are using the recycled water, always trial with few plants first. Maybe you can have a zone, put 20 different type of plant that you grow or that your landscape has, spray in there, see which plant is having damage, and then you can select and apply in the plant that is not having damage. So these are the way how you can mitigate risk. Also, As I told, we can have a constructed wetland before we collect the water to retention pond. Or if you are not having that retention pond, you can have a constructed wetland with plants, with a lot of different plants, and those plants will clear out the pesticide, and then you dump those water to the drain or river or wherever it goes to the wetland. Also, sand filters are cool. So sand filters create a thin biofilm above the so it creates a biofilm above the sand layer, and then those biofilm has the microbes that can degrade the pesticide. So if you have a big tank with a pond, just let the water pass through that pond, which is the sand filtration, and then that way with adsorption and microbial degradation, you can reduce pesticides. Also bioreactors, we can build a bioreactor based on pine bark or other high CN based materials and let the water sit in there before we use it. And all these things, we will have an expert in this field talking about these techniques in depth in our future webinars, but I just wanted to give you just a brief introduction to those. And with that, let's wind up. So when winding up, we know that there are a lot of problems that might be associated with the retention pond. Pathogens and disease are one of the crucial things, and we'll have a subject matter expert to talk on those topics in future. The second thing is agrochemicals and pesticide. We know nitrate and phosphate, and their concentration in retention pond might be good, might be bad, depending on type of your operation, and we know how to reduce it. We also know pesticide type, plant growth stage, dose of pesticide concentration might play a role in how it affects plants. We need to consider that. And when we are considering pesticide properties are essential thing to consider, and that can be easily found out by Googling safety data sheet or material data sheet. If we have pesticide in our pond, retention pond, and if that is causing problem, there are ways to mitigate those risks. And with that, I would like to conclude the presentation. And after this, after the end of the webinar, there will be a survey. Please feel free to fill out the survey. And if you have any questions, I am taking it right now.